Hello, welcome back to PhysioDesigner tutorial series. In this tutorial series, we are going to create a multi-timescale adaptive threshold model receiving a spike train input, which is one of models of neuron membrane potential, on PhysioDesigner. Abbreviating the model name, we call this a MAD model. Dividing into a couple of movies, we will create a MAD model piece by piece. In this movie, we are going to create a cell body, that is, a MAD model itself, including the membrane potential and dynamic threshold. Alright, before starting to build a model, we'll show a simple explanation of the MAD model. A MAD model does not consider a shape of each spike, which is created by rapid depolarization followed by rapid repolarization and undershoot with a refractory period. It is contrasting to Hodgkin-Huxley model, which reproduces continuous spike shapes with rapid dynamics. If you consider spike patterns, that is timing of spike occurrences, from the viewpoint of signal processing in brain, such a rapid dynamics can be neglected, and it's enough to consider the after-spike dynamics corresponding to undershoot and refractoriness. In this sense, a MAD model is in the same model class with a leaky integrate and fire model. In those models, when the membrane potential touches the threshold, it is considered as a spike occurrence, and a resetting corresponding to the repolarization and overshoot occurs. In the case of a leaky integrate and fire model, its threshold is a constant value, and after spike resetting on the membrane potential is considered. In contrast, in the case of a MAD model, its threshold is dynamic, and after spike resetting happens on the threshold. Multi-timescale means that the decay of the threshold after resetting is defined by multiple exponential functions. The dynamics of the model is defined by these equations. The dynamics of the membrane potential is composed of a simple leak and external input current terms. The threshold theta is a summation of a base value omega, and two variables h1 and h2. h1 and h2 show simple exponential decays, but with different time constants, and after a spike occurrence, that is v is greater than and equal to theta, h1 and h2 jump by alpha 1 and alpha 2, respectively. Okay, then let's implement these equations on PhysioDesigner. We will create two modules for the membrane and the threshold. Finally, we will create a module which detects threshold crossing of the membrane potential and outputs a spike train. Let's begin with creating a membrane potential module and open a physical quantity dialog. The first physical quantity we create is V, whose type is state. Let's set 10 for the initial value. The implementation of the ODE is diff v time equals 2 minus v plus rai sin over tau m. Those physical quantities used in the right-hand side of the equation are not defined yet, so it asks if you want to create their entries automatically. Click yes. They are created as static parameters. The value of r is 50. A is 0.15. ISIN should be a variable type to receive the value from outside. At the base setting tab, change its type to variable parameter, and at the implementation tab, definition type is assign, and set a name to create a new import. The last physical quantity tau m is of the static parameter, and its value is 5. Finally, let's define the output of this module. It is V. Go back to V, and at the base setting tab, set a name to create a new output at the right-hand area of the dialog, and select the new output in the list. That's all for this module. Click OK button, and close the dialog. Next, we will create a module for the threshold. We begin with a variable parameter type physical quantity, theta. This is defined by a summation of omega, h1, and h2. Click yes button again. Omega is a static parameter representing a base threshold, and its value is 19. Next, select h1. This is a dynamical variable defining the adaptive threshold. Hence, we need to change its type to state at the Basic Setting tab. Let's set the initial value 10. The implementation of ODE is simple. It is -h1 over tau1. Then, we need to define the after spike resetting on h1. Go to Extra Implementation tab and select Conditional for the definition type. Threshold touching of the membrane potential can be detected by a condition V is greater than equal to theta. When the condition is satisfied, alpha 1 is added directly to h1. Similarly, define dynamics of h2. Change the type to state. Its initial value is 20 here. Time constant is tau2. And after spike jump width is alpha 2. Next, tau1 is 10. V is a variable parameter receiving the value from outside. Change the type to variable parameter, and at the Implementation tab, Definition type is assign. Set a name of the new import. Then, set values for 3 static parameters. Alpha 1 is 37. Tau 2 is 200. And alpha 2 is 2. Finally, define an output of this module, which is theta. Go back to theta. And at the Basic Setting tab right area, set a name and create a new output, and select it. Alright, that's all for this module. Click OK button to close the dialog. Linking a functional edge from an output V of the membrane potential module to an import of the threshold module, the main part of a MAT model is completed. Next, we are going to create a module that detects threshold touching of the membrane potential and outputs a spike train. In this module, at first we create a physical quantity, which represents spike occurrences. Name is MAT spike, and its type is variable parameter. The definition type is conditional, at the Implementation tab. If a condition that V is greater than or equal to theta is satisfied, MAT spike will be 1, meaning there is a spike. Otherwise, MAT spike is 0, meaning no spike. V and theta are variable type, receiving the values from outside. Hence, again, at the Implementation tab, new import for each physical quantity has to be created. Similarly for theta. Change the type to variable parameter. Select Assign, and create a new import. The output of this module is a spike train. Hence, go back to MAT spike and create a new output, and make an association with it. After closing the physical quantity dialog, link edges from the membrane potential module and threshold module to the spike detection module. Finally, let's encapsulate these 3 modules. Clicking left mouse button on these mouses with pressing command button, we can select multiple modules. Then right-click on one selected module, and select Encapsulate in the menus. Change the name of the capsule module properly. Then, prepare an import and an output on the capsule module, which act like the interface. Link a forwarding edge from an output of the spike module to the output of the capsule module, and a forwarding edge from the import of the capsule module to the one of the membrane potential module. Good job everyone, let's save the model now. Set the model name, and set the file name. Now, it's a good time to run a simulation. To do that, we need to prepare inputs to the MAT model. We can use the Poisson spike generator and postsynaptic current generator that we created in the previous tutorial. We can add those model to this canvas. In the menu bar, select File and Add Model, and select a postsynaptic current generator model. The two modules linked by a functional edge are added. Besides the postsynaptic current generator, a Poisson spike generator is also included here, because last time we created this model, we already added the Poisson spike generator model and saved. For running a simulation, link a functional edge from the output of the postsynaptic current generator module to the input of the mat capsule module. Alright, the model is completed now. Save it, and let's run a simulation. Call Flint from Simulation menu. Let's set 300 to the simulation length, click Run button. We will observe the input spike train, postsynaptic current, membrane potential, adaptive threshold, and output spikes. Everything is calculated correctly. Then next, try a little bit larger gain to calculate the membrane potential. Now it is 0.3. And let's observe the same physical quantities. By comparing these two, obviously the second simulation produced more spikes. This is because the higher gain yielded larger membrane potential in average. Alright, that's all for this tutorial. Thank you for watching. Hope to see you in the next tutorial. Goodbye.